right, welcome to another podcast. In this episode, we're going to be taking a look at the forward version of the Fourier transform. Just to remind you of what that looks like, the forward version would be taking a function f of t and turning it into, via the Fourier transform, this function f of nu that we talked about in the previous video that stores all the information. So this is the decomposing part rather than the putting or piecing back together part. What I want to do now is basically look at a question that is sort of related to this, because what we're looking at in this particular video is how do we take a time signal and decompose it into frequencies. And I kind of want to look at a related question with you. So the related question here is, how many $5 bills compose or make up a $100 bill? Well, in terms of sheer value, I think answer-wise, it would be very easy to suggest that we just take $100, divide it by 5, and you would tell me that there are 20 $5 bills in each $100 bill. In that way, what we've done is very similar to what I'm about to do. The $5 bill is sort of forming what we would call the frequency, because we could look at other frequencies. We could look at $1 bill frequencies, we could look at $10 bill frequencies, $20 bill frequencies, etc. And then this gives me how many of them there are in that frequency, and this is kind of like the amplitude of the corresponding frequency. Well, if I then want to take this and compare it with the question at hand, the basic idea that I'm after is a very similar question, and that is how many sinusoids of frequency nu make up the signal f of t. Well, I'm going to actually answer this in the same way, believe it or not. I'm going to take my function f of t and divide it by the format that we discussed in the previous video for sinusoids of frequency nu in the complex plane. And it looks like this. And we understand that that is the same as this. And so this is a, if you want to think of it, then f of t is kind of playing the role of the amplitude. It's not really playing the role of the amplitude. It's sort of like doing the decomposing, right? It's the how many parts, maybe is the better way to say it. This is the yeah, I can think of it as the part with frequency given by this guy. And so all we would do at that point is that we would sum continuously over all such pairings, which are based on the frequencies. And what you wind up with is you wind up with a decomposition of the function in the following form. Basically, I would look at something of this form. And I would sum over all possible frequencies rather than all possible times, as we did in the previous video. And the resulting thing that you get is a list of several things. This gives info about f of t's component frequencies, amplitudes, and phases. And as we talked in the last video, those three things combined are what we need to restore the signal, but this process breaks it down because it basically takes f of t and divides out the frequency part. We then store all that information through the summation of the integral into one function, which we call the Fourier transform. And so there are several remarks here. The first one is kind of maybe pictorially what's going on. If I take this integral from minus infinity to infinity of f of t e to the minus I 2 pi nu t d nu, then here's what this process is representing in some way. I take an arbitrary signal, f of t, and I decompose it, or I better, maybe given what we've talked about here, maybe the better way to think of it is I divide it. I divide it by a standard, let's give a number here, let's say 15 hertz frequency wave. So, this say a 15 hertz frequency wave, and the result of that is the function f at 15. This stores the amplitude and phase needed to replicate that part of f of t, which is like a 15 hertz wave. So it's storing not only the fact that there are 20 $5 bills that are needed, it's storing what the offset is in terms of the representation. So that briefly describes the picture. What are some of the other points to this? Well, if I'm looking at the Fourier transform of a function f of t, our notation for that is capital F, just like it was capital L for the Laplace transform. So capital F of nu, or sometimes the notation with the little hat symbol is used as well, so be aware of that. And just some remarks that I have about that. First off, if I tell you the absolute value of the Fourier transform, this is the amount of frequency nu present in the original signal f of t. And when you look at the phrasing here, the amount of frequency nu, you should interpret that as a saying something about the amplitude at that frequency. Okay, I could also look at the imaginary part of this function, and remember, f of nu is complex, potentially. If I looked at its imaginary part, this would represent the phase offset of the base harmonic in that frequency. Now, let me create just a little bit more room here because there's something else that needs to be said. And we'll call this remark number 3. Functions or signals that are compressed, sometimes you would say localized, in the time domain, are spread across the frequency domain. Meaning that if you give me a function f of t that's tightly packed or compressed, then its Fourier transform, once graphed, is going to be very spread out. And this is because, since it takes higher frequencies to describe such a signal. Now the reverse of this is true as well. If the original signal is very spread out, so it has a rather large frequency, then the resulting frequency domain is going to be very tightly packed because it will only need those waves with very low frequencies to describe it. So they're sort of inversely related in terms of spread of the functions that are involved. This phenomenon is called the uncertainty principle. So if you've heard that described before, the uncertainty principle, this is a principle that is applied to the fact that what happens in the time domain and what happens in the frequency domain are fundamentally sort of at odds with one another. And we're going to explore that idea thoroughly here in class over Fourier transforms, as well as on into when we do Fourier series. But this is just a small look at what it means to find a Fourier transform. What is the Fourier transform? What information does it contain? What does it tell you? And then in the previous video, we looked at how to reverse the process. And both are very telling of the structure of the transform geometrically in terms of what it's trying to do. All right, thank you for watching.